Hi there, and welcome to this lesson on Pure Mathematics 1. And in this lesson, we'll be considering the gradient of a curve. And the reason for the lesson is it's very much preparation for the next lesson when we'll meet differentiation for the first time. Now, we discovered in an earlier lesson that if you have a straight line, then the gradient is given by the change in y divided by the change in x between any 2 points on that line. And you can write the gradient as m, that's the letter normally used. It is the change in y over the change in x. And that's sometimes written as delta y over delta x. The Greek letter delta normally means change in something, change in some value. And the normal formula is y2 minus y1, the change in y, divided by x2 minus x1, the change in x. Now, what about if you have a curve? Well, the first thing to say is if you have a curve, then the gradient is constantly changing. If you imagine that you were cycling along this as a hill, then the steepness of the hill is constantly changing, gradually getting less steep as you get to the top of this little bit, then going downhill, getting steeper and steeper, then getting less steep, then starting to go uphill, steeper and steeper. But the gradient is changing continually. How do you calculate the gradient at any point on the curve? Well, let's choose a point A. The gradient is the gradient of the tangent at that point. So if I was to draw the one line that touches the curve at that point, but doesn't cross it at all, the tangent, and work out how steep that line is, then I will also have found how steep the curve is at that point. To calculate the gradient of the tangent, you choose any 2 points on the tangent, and then you find the change in y and the change in x between those 2 points. And after you've done that, you calculate the gradient in the normal way. Okay, what have we just been saying then? If you want to know the gradient of the curve at the point A, what you actually do is you find the gradient of the tangent at the point A, which would be equal to the change in y over the change in x between any 2 points on that tangent. Now, one way you could do this is by drawing a graph as accurately as you can, and then measuring the change in x, the change in y, and just working out the gradient by putting the numbers into the formula. Or it's possible to do better than that. If you choose 2 points on the curve close to A, so choose A and then choose a second point very near to it, it's possible to calculate the gradient to any accuracy that you choose. So for example, let's say you had the curve y equals x cubed minus x squared minus 6, and we had the point A 2 minus 8, and we wanted to know the gradient at that point. Well, to estimate the gradient at x equals 2, what we do is we choose a second point which is close to A. So A is at x equals 2. I could choose the point B at x equals 2.5, which would be the point there. And then what I do is draw the line through A and B. Now, when I've done that, I don't have the tangent at A, which is why this doesn't give me a perfect answer. But what I do have is a line which is very close to the tangent. To work out the gradient of that line, I need to know the y value at B. I already know the x value. We chose 2.5. To work out the y value, I just substitute x equals 2.5 into the original equation of the curve. That would give me that. Put that in the calculator, and that gives me a y value of minus 5.625. So I now know the coordinates of A and the coordinates of B. A is 2 minus 8. B is 2.5 minus 5.625. That's these 2 points here. And the gradient of the line that goes through those 2 points is the change in y over the change in x, just in the normal way, which gives me minus 5.625. Take away the minus 8 over 2.5 minus 2, which simplifies to that, which gives me 4.75 for the gradient. So that is an estimate for the gradient of the curve. It's exactly the gradient of that line, but that line isn't exactly the tangent. but it is an estimate for the gradient of the curve at x equals 2. And if I want a more accurate estimate, all I have to do is move the point B closer and closer and closer to A. And as I move the point B closer to A, then the line through A and B gets closer and closer to being the tangent, which means the gradient of that line gets closer and closer to being the gradient of the curve. Now, I'll let you have a go at working out what this means in practice. So we just looked at the point where x equals 2.5 and worked out what the gradient of that line would be. Example 2, you've got 3 questions, and we're moving this point closer and closer to B. So first of all, we'll try at x equals 2.1. You'll need to work out the value of y using the equation for the line, and then you need to work out the gradient of the line through A and B in the normal way. Do the same thing again when we get closer still to x equals 2.01, and then do the same thing again a third time when we're now extremely close to the point A, where B equals 2.001. Okay, I'll let you have a go at this. So pause the video, have a go, and then come back to me again when you're ready. Okay, let's have a look. Now we do exactly the same thing as we did in example 1. So if x equals 2.1, the first thing we have to do is work out the value of y. So substituting 2.1 into this equation gives us a value of y of minus 7.749, which gives us the coordinates of A and the coordinates of B. We then work out the gradient of the line through A and B in the normal way, change in y over the change in x, which would give us that. Put all that in the calculator, and you get a gradient of 2.510. Then we do the same thing again for x equals 2.01. So first of all, we substitute 2.01 into the equation of the curve, and that'll give us the value of y. Put all that in the calculator, and you get a value of minus 7.979499 for y. Now we know the coordinates of A and B, so we can work out the gradient of the line through them in the normal way. Those are the numbers you need to put in the calculator, and for the answer you should get out 2.051 to 3 significant figures, or 3 decimal places. Third example was exactly the same idea, but now we're extremely close to the point A. So A is at 2 and B is at 2.001. So the line that we'll get will be very, very close to the tangent. We work out the y value in the normal way, and this time you get minus 7.997995. We work out the gradient in the normal way, now that we know the coordinates. That will give us this when you put the numbers in the calculator, which gives us 2.005 for the gradient. Okay, we've just done the same thing 4 times, with points getting closer and closer to A. First of all, when we choose x equals 2.5 for the point B, we've got a gradient of 4.75. Then when we move to 2.1, then the gradient of that line was 2.510. When we moved to 2.01, the gradient was 2.051. And when we moved to 2.001, then the gradient of the line joining A and B was 2.005. It looks like these are tending towards a limit. So it appears that x equals 2.5, the first point, that point was just too far away from A. And when I work out the gradient of it, that is correct, but it's nowhere near the gradient of the tangent, that we needed a point closer to A. However, it also appears that as this point B approaches A and gets closer and closer, the gradient looks like it's tending towards a limit. And it looks like it's tending towards the limit of 2 for the gradient. Okay, we'll stop there. Now, in the next lesson, we'll see where this idea leads and how it leads us towards differentiation. So that is the end of the lesson. If you've got the textbook, then turn to page 153 and have a go at exercise 8A. Thank you very much for listening, and cheerio.